Welcome to GERO Mathematics and Statistics lessons. In this video, I'm going to be discussing other ways to obtain the arithmetic mean. I'm going to be discussing other ways to obtain the arithmetic mean besides the normal method. Okay, so that will be the focus of my part 2 video on measures of central tendency, other ways to obtain the arithmetic mean besides the normal method. Okay, so let us now go to what we had explained earlier on as the normal method for obtaining the arithmetic mean. Okay, so what we are referring to as the normal method is what I want to explain now. Now remember, for a data set comprising x1, x2, x3 up to xn data entries, remember that we said what we call the arithmetic mean for this data set will be represented with x bar. That was our starting statement. Now, there were three categories we explained on which the arithmetic mean depends. The way to obtain your arithmetic mean depends on, okay? So there were three categories. Category number 1 was for what we called case 1. It was for a case with no frequency in the data set. So if there was no frequency in this data set, x1, x2 up to xn, then we discussed that this will be the arithmetic mean. X bar will be the summation from I equals 1 to n of all the xi's all over n. So that was how we defined the arithmetic mean for that case. For a case 2, that is a case with frequencies. For a case with frequencies in a small data set, we defined, that is, if there were frequencies in this data set, we defined the arithmetic mean x bar to be the summation from I equals 1 to n of all fixi's all over summation all fi's from I equals 1 to n. And remember, in this particular definition, our xi was actually referring to the data entries themselves, and our fi was representing frequencies of each data entry. So by frequency of each data entry, we actually mean that the number of times each data entry reoccurred. So that was our case 2 for what we call the normal method. Okay, now for our case 3, it was a case with frequencies. It was a case with frequencies in a large data set. Okay, that is when this is large. Take note, for a case with small, this was for a case with small data set, meaning that n was presumed to be less than 30. And for a case with a large data set, n, our size of the data set, was presumably greater than or equal to 30. Now, for this particular case, we defined the arithmetic mean x bar as the summation from I equals 1 to n of all fi xi all over summation fi from I equals 1 to n. And in this case, our xi was defined not as the data entry, but as the class mark. The class marks, okay? These were the class marks, and our fi's were defined as the frequencies, not for the data entries, but the frequencies of each class interval or class mark. Okay, so by this we mean that the frequencies were actually representing the number of data entries in a class interval. So that was put together. These formula were called the normal method for obtaining the arithmetic mean. So what are we to do in this video, which is a part 2 video on measures of central tendency? So in this part 2 video, what I want to do is to explain other ways to obtain the arithmetic mean. Okay, now the first method we are going to be looking at is called the assumed mean method. The assumed mean method. Okay, so I'm going to paint a scenario of how this method works, or what gives rise to this method in this video. Okay, so let us start with this. Let us start with an illustration. It will do us a very great good, okay, before we go into the development. So I'm going to bring back an example. Let's bring an example of this. Let's assume we have a group of individuals. So there are several individuals in this group, and I'm using my green colored pen to represent the individuals. Now there is an individual in this group that represents this group. So the red colored pen is for the leader of the group. So we have the leader of this group representing the entire members of the group. Now let's assume that this guy was produced by a measure of central tendency, and in particular the measure of central tendency that produced this guy is the arithmetic mean. Okay, what we want to do is to illustrate something. What is called the assumed mean is a mean that stands in the place of the actual arithmetic mean. So this guy is the actual arithmetic mean, but if it so happens that this guy falls sick, if this guy falls sick and is unable to attend to the matters of the group in terms of representing them, it is very possible that we may end up choosing from this data set another person. I'm circling this guy. So this person who we choose now becomes an assistant, or what we can now call an assumed class rep. Okay, so let me explain again. Now, in the real sense, there was a guy in this group who represented the class, but something happened to this guy painted in red who represents the class, and that prompted a need for somebody to assume his role as a representative. Now, the person who assumes his role as a representative is now called the assumed class rep. while this guy painted in red is the real class rep. Okay, so that brings me to the development. Now, so it all starts with having a data entry xi. It starts with having a data entry xi, okay? And I want you to follow this properly. So you would notice that each of them, I could call this one x1, I could call this guy x2, this guy I could call x3, this one I could call x4, this I could call x5, this I could call x6, okay? Now, take note of one thing. Because every member of this set is used to this guy, and he happens not to be around, for that reason, somebody assumed his role, the person we are now calling the assumed class rep. He is not the true class rep, but is only assuming the role of a class rep. So, because of something happened to this guy, so we have chosen the assumed class rep. Now, take note, because he is not the real class rep, there is, for every individual in that group, a corresponding gap I'm going to call di. Okay? Take note, this is not a subtraction sign. This is, okay, in better still, let me put this. So, for every data entry in the data set, there is a corresponding deviation. Now, when the class rep was there representing the class, there was no deviation, meaning that everybody in the class were used to the class rep, the real class rep, and they had no misunderstanding with him. They had no rancor with him. So everybody had a gap, a zero gap between themselves and the class rep. That is just an illustration. It's an assumption. But because someone was now assuming his role as an assumed class rep, there are now deviations. So, this assumed class rep, we shall use the symbol or the letter A to represent this assumed class rep. If to every data entry, because of the assumed class rep, there is a deviation from the assumed class rep, then what it means is that we now have a gap di equal to xi minus a. And that is where my development begins. And I want you to follow the story properly. So my development begins with taking note of this. So I'm going to give an illustration here. x1 will be away from this assumed class rep by a gap d1. Okay? x2 will be away from this assumed class rep by a gap d2. Why are they having gaps between themselves and the class rep? It is because they are not yet used to the new guy. So there are gaps. Misunderstanding gaps, rancor gaps, quarreling gaps, not understanding the class rep gap. So there are different gaps. Okay? Now, we are using D's to represent the gaps. So for D3, there will be a corresponding x3 minus a gap. And that will continue if you had up to n data entries, you have xn minus a. Now take note, my DIs are changing, my gaps are changing, my data entries are changing, but my A's are not. All my A's are constant. So the assumed class rep remains fixed, but the gaps are changing because away from the assumed class reps are different gaps. So what we end up having is, say the class rep, the assumed class rep this, and every other person in the data set. If this is D1, the gap between this will be D1 and this will be X1. So the gap between A and X1 is D1. If there's another guy in the class we call x2, the gap between A and x2 will be d2. If there's another guy in the class we call x3, the gap between A and this guy will be d3, and so on. It continues. If there's another guy d4 or x4, the gap will be d4. Okay, so now having painted that picture, let us now go into the development. Okay, so how do we develop a formula for calculating the arithmetic mean if we are given what is called an assumed mean? So it starts, please follow me, it starts with taking my di's. So di is equal to xi minus a. Okay, now if di is equal to x minus a by the explanation I've just given, let's in this case take note we are considering a case without frequencies. Let's start with considering a case without frequencies. So this would imply that I can make xi my subject of formula, and that will give me di plus a when I make xi my subject of formula. Okay, so if there are no frequencies, then what it will mean will be that I can take the summation of both sides from I equals 1 to n. If I take the summation of the left hand side of this equation, it will require me to take the summation from I equals 1 to n of the right hand side, and that will give me this. Okay, now this would mean I have summation from I equals 1 to n of xi equals, summation would go into this bracket, opening it up, and that would mean I equals 1 to n of di plus summation from I equals 1 to n of my a's. Okay, now take note of this. When you sum a constant, a is a constant, di is iterating, xi is iterating. Now, if you add as an illustration 5, which is a constant, to itself 3 times, this will give you n times 5. So in this case precisely, there are 3 5s, so this will be 3 times 5, giving you 15. Now, I'm going to bring that idea here. I'm going to bring that idea over here. So if you sum a, which is a constant, n times, the result will be n times a. But this is not a constant, so it remains summation of all di's from I equals 1 to n. And this remains summation of all xi's from I equals 1 to a. So this equation implies this. Okay, now the next thing we are going to do to this last step is to take or rather is to divide. We are going to divide both sides by n. Okay, so let us divide both sides by n. When you do, this will be summation from I equals 1 to n of all xi's divided by n equals summation from I equals 1 to n of all di's plus n a divided by n. Okay, now take note, by simple rule of algebra, a plus b all over c is the same as a over c plus b over c. Okay, so by this simple rule of algebra, we would end up having the right hand side becoming this, from I equals 1 to n di n a all over n all over n. And take note of this. This was our very definition of x bar. Okay? Now on this other side, n cancels n, and we are left with x bar equals summation from I equals 1 to n of all di's all over n plus a. Now, take note, when we had summation of all xi's all over n, it was called x bar. So we can apply the same routine here by saying summation of all di's all over n can be called d bar. So what we have just established is a formula that helps you compute the arithmetic mean for a data set when you are given an assumed mean a, and in particular the data set has no frequency. So this helps to compute the arithmetic mean, okay, the arithmetic mean when provided the assumed mean. Okay, when provided the assumed mean for a data set with no frequency. Full stop. Okay, so go over it again. That was for the case with no frequency. Now let's go to the case with frequencies. What if we were asked to compute the arithmetic mean for a case with frequencies? Let's repeat the routine again. So it all starts with our di equals xi minus a. Okay, so this is for a case with frequencies. Okay, it's for a case with frequencies. So it all starts from here. Now what we are going to do is to make xi the subject of formula. When we make xi the subject of formula, we are going to have di plus a. Okay, now the next step to take will be to multiply both sides by frequencies, and that will mean fi times xi on this part, and that would imply fi times di plus a in bracket. Now if I continue this procedure, this will be fi xi equals fi multiplies di to give fi di, fi multiplies a to give fi a. Now at this point I can now take the summation from I equals 1 to n of both sides, and that will give me fi xi summed up from I equals 1 to n equals summation from I equals 1 to n of fi di plus fi a. Now the next thing to do will be to divide both sides, or let's simplify first of all. So if I simplify, this would go, the summation would open up the bracket as a linear operator, and that would give us fi di in the first case. But take note, for the second case, it will bring out a and operate on I. For I equals 1 to n, it will operate on fi. Now let me explain what is actually going on there. Take note, if I have 5x plus 5x plus 5x, it is the same as having 5 in bracket x plus x plus x. So if I call this x1, let's assume that the x's are different, and I call this x3. This will be 5 times x1, x2, x3 adding themselves, And that, by our notation on summation, will be 5 times summation from I equals 1 to 3, 1, 2, 3 of all xi. So what is actually going on here is that when the summation, being a linear operator, operates on this, it will bring out the constant a and only implement or affect rather fi. So that is what brought us to this point, okay? Now the next thing we are going to do is to divide both sides by, we are going to divide both sides by summation fi from I equals 1 to n. When we do that, it will give us summation from I equals 1 to n fi xi all over summation fi from I equals 1 to n equals summation from I equals 1 to n fi di plus a summation I equals 1 to n fi, all these over summation fi from I equals 1 to n. Okay, that is what we shall obtain. Now, by that same rule of algebra, that a plus b all over c equals a over c plus b over c. By this same rule of algebra, we are going to have this. Take note, everything here defines the arithmetic mean for a case with frequency. So that is x bar, okay? Now, on this other part, we are going to have summation from I equals 1 to n fi di all over summation from I equals 1 to n fi added to a summation fi from I equals 1 to n all over summation fi from I equals 1 to n. Now take note, this will cancel this because they are the same, and our result will become x bar equals summation from I equals 1 to n fi di all over summation fi from I equals 1 to n plus a. Again, summarily, this whole thing here can be written as d bar. So we have d bar plus a, giving us the same result but different procedure for a case with frequencies. Okay, when you want to obtain the arithmetic mean for a case with frequencies when given the assumed mean. So take note of this. So this is another method for obtaining the arithmetic mean. Okay, now let us go to, so the first alternative for obtaining the arithmetic mean is with the method of assumed mean. Okay, now I'm going to, before I go into the next method, I want to state here that the assumed mean method is used as an alternative for obtaining the arithmetic mean. Okay, it is used as an alternative for obtaining the arithmetic mean in cases where the data entries are large. Okay, hence making computation difficult. So when the data entries are large and makes your computational process for obtaining the arithmetic mean difficult or complex, you can now define for yourself an assumed mean. An assumed mean will reduce the data entries to something smaller you can manage, okay? So I'm going to stop there, but we are going to take an example, but not yet. Let us now go into discussing the next method. The next method is called the coded factor method. The coded factor method. Okay, so the question is this: what prompts the coded factor method is, now that we have said this about the assumed mean, that is, it is useful when the data entries are large and you want them reduced so as to make computation that was difficult when they were large to become less complex or less difficult when they are now reduced. What happens if after that reduction the data entries are still large? So I'm going to start with saying the coded factor method becomes useful in computing the arithmetic mean. Becomes useful in computing the arithmetic mean if reduction in the size or the sizes of data entries, if reduction in the size of data entries remain large after using the assumed mean. Okay, so if after using the assumed mean to reduce your data entries to smaller values that you can manage in computing your arithmetic mean, the data set is still large, the better method to use will be the coded factor method as an alternative. So let us now go into the development of the coded factor. So we shall start as usual for a case with no frequencies. Okay, so let's start now. The coded factor is represented, the coded factor is represented with the variable ui. Okay, we use ui to represent the variable, and it is defined as ui equals di all over c. So take note, the ui here is called the coded factor. Okay, we call ui the coded factor. Di remains as defined earlier on. It remains deviations from A, the assumed mean. And C here represents the class size or class width if we are talking about a group frequency distribution, but it may be any defined number if we are talking about an ungroup frequency distribution. So your C would be any defined number if we are talking about an ungroup frequency distribution. But if it is for a group frequency distribution, it will bear the name class size or class width. Okay, so let us now go straight into the development. Now let me take this part off. Okay, so let us see, it all begins with ui equals di over c. Okay, now what was our di? Remember, our di was the same as xi minus a. So I'm using xi minus a to represent our di as we defined it earlier during our discussion on assumed mean method. So the first thing I'm going to do is to make UIC the subject of formula. So when you cross multiply, you're going to have UIC on the left hand side equals xi minus a. Okay? When we make xi the subject of formula, we are going to have uic plus a. Okay? So now, because we are discussing the coded factor method for a case with no frequencies, we are going to start with here taking summation from I equals 1 to n of xi, and that would imply taking summation from I equals 1 to n of everything here plus a, okay? And that will give us summation from I equals 1 to n xi equals summation from I equals 1 to n of ui times c plus summation from I equals 1 to n of a. Okay? Now, as it continues, you would notice that here, because c is a constant, the class size, it comes out from the linear operator, the sigma here, the summation, and we have ui being operated on. And this would give us na on the other hand, because we are adding a constant n times. So this is summation from I equals 1 to n xi. Okay? Now, if we proceed further, we are going to have, on dividing both sides by n, we are going to have summation from I equals 1 to n of all xi's divided by n. We are going to have over here, let me bring this over here, we are going to have this c summation from I equals 1 to n of all ui's all over n plus na all over n, if you remember what we have been doing. So n will cancel n, and this will leave us with c in bracket summation from I equals 1 to n ui all over n plus a, and this on the left hand side defines x bar. So if x bar is defined as summation from I equals 1 to n of all xi's all over n, then it means what we have in this bracket can also be defined as u bar. So x bar equals cu bar plus a becomes our arithmetic mean. It becomes our arithmetic mean for a case with no frequencies using the coded factor method. Okay? Now, what if what we were given was a data set with frequencies? How do we obtain the coded the arithmetic mean using the coded factor method? So we begin again with ui equals di over a, just like we started that one. Now this will give you ui equals xi minus a, because di okay, sorry, this was c, di over c, so this will be xi minus a all over c. Okay, now we would make uic the subject of formula by cross multiplication, and this will leave us with xi minus a. Okay, the next step was to make xi the subject of formula, and that will give us uic plus a. Okay, since we are dealing with a case with frequencies, we are going to take summation, or we are going to multiply frequencies to the left and to the right, and that will give us fi in bracket uic plus a. Okay, now if we proceed further, fi xi is what we have over here, and it will multiply this to give us fiuic, and if it multiplies this, it will give us fia. Now this gives us, when we take the summation of both sides from I equals 1 to n, fi xi, this will be taking the summation from I equals 1 to n to maintain that balance. It will be taking the summation of fiuic plus fia. Okay, this will give us summation from I equals 1 to n fixi equals, now this summation opens up this bracket and it gives us this I equals 1 to n. C comes out as a constant, leaving us with fiui as those variables are iterating. So this will give us A coming out with sigma operating on fi, okay, for the same reason. Now, if we go on to divide both sides, if we go on to dividing both sides by summation fi from I equals 1 to n, then we are going to have summation fixi from I equals 1 to n all over summation fi from I equals 1 to n on the left hand side. So we are going to have this on the left hand side, okay? Now, if you come over here, this will be C summation from I equals 1 to n of fiui plus A summation fi from I equals 1 to n, all divided by summation fi from I equals 1 to n. Okay, now let's bring it over here, our continuation. So everything on the left hand side, everything there defines the arithmetic mean, x bar. So I'm going to write here x bar equals, this becomes C summation fiui from I equals 1 to n all over summation fi from I equals 1 to n plus A summation fi from I equals 1 to n all over summation fi from I equals 1 to n. So this will cancel this because they are the same, and we will be left with x bar. Here we can now write this as C in bracket summation fiui from I equals 1 to n all over summation fi from I equals 1 to n plus A. Take note, everything inside this bracket can be written as u bar. So the result we have from this development is this, and this becomes the arithmetic mean for a case with frequencies when you are given the coded factor, for a case with frequencies and the coded factor. Okay, now let us quickly go into taking an example that shows how to obtain the assume mean method, obtain the arithmetic mean using the assume mean method and the coded factor method, okay, to round up this class. Now, so I'm putting up an example here. I'm going to call this my example 1 in this video, okay? So the question says obtain the arithmetic mean for the data set using the coded or using the assumed mean method, and coded factor method. Okay, so the hint is A is equal to 5. So we are giving A the assumed mean as 5, and class size, in this case, let's assume we are told our class size is 3. Okay, let's assume that our class size is 3. So now let's have this, an already prepared data set. Let's have this, an already organized data set giving us this frequency table. So I'm going to put here class interval. So I'm going to have here 1 to 3. So okay, so 1, 2, 3. I'm going to have the next as let me have the next as 4 to 6, and the next as 7 to 9. Okay, so let's assume we have these 3 intervals. This will give us corresponding class marks. So the class mark for this interval will be 1 plus 3 divided by 2. So 1 plus 3 is 4. 4 divided by 2 will give you 2. So if you add 2 to the class size of 3, this will give you 5. Add 5 and to 3, this will give you 8. Okay, so these are the class marks. Now, then, because let's look at the case. I'm starting with the case of frequencies. Okay, so let's put this now. Let's assume that the frequency here is 15, the frequency here is 10, and the frequency here is 5. Okay, now ordinarily what we are going to obtain, this will be summation of from I equals 1 to 3, because there are 3 frequencies, 1, 2, 3. This will give us summation Fi equals 15 plus 10, which is 25 plus 5, which is 30. Okay, so the summation of all Fi's would have given us 30 over there. Now, for us to compute the mean using the normal method, because I want you to see how we compare, Fixi will give us 2 times 15, which is 30. 5 times 10 will give us 50. 8 times 5 will give us 40. So what we would have had will be summation Fixi from I equals 1 to 3 is the sum of 30, 50, and 40. So that would have given us a total of 80 plus 40, which is 120. Okay, so in this case, our x bar using the normal method would have been summation from I equals 1 to 3 of Fixi all over summation Fi from I equals 1 to 3. So this will give you 120 all over 30, and that will reduce to 4. So the mean will be 4 using the normal method. Okay, now if you move over, I'm going to extend this. Now I'm extending this because the question demands that we use the arithmetic, we obtain the arithmetic mean using the assumed mean method and the coded factor method, and we have been given a coded factor of 5 and a class size of 3. Okay, so now the first thing, let us consider getting the mean using, so I'm going to call this I for we have obtained the mean using the normal method. Okay, so what we want to do here is to obtain the mean using the assumed mean method. So I'm going to start with computing my di's. Okay, my di will be xi minus a. Now, xi minus a simply means each of these xi's will be subtracted, or you will be subtracting a being 5 from each of these xi's. So this will be 2 minus 5, giving me minus 3. This will be 5 minus 5, giving me 0. This will be 8 minus 5, giving me 3. Okay, so that implies that the di's, the summation from I equals 1. Okay, I'm not going to add my di's. I'm going to go over to frequencies, because this is a group frequency distribution, so there are frequencies. Now I'm going to compute, after computing my di's, I'm going to compute FIDI. So I'll create a colon for FIDI. Now under this colon for FIDI, I'll be using each of my di's to multiply my corresponding frequency. So 15 times minus 3 will give us minus 45. 0, the di here, times 5 will give us 0. 3, the di here, 0 times 10, the frequency here will give us 0. So that was my mistake, okay? My bad, sorry. So 3 here times 5 will give us 15, and this will become plus 15, okay? So now minus 45 plus 0 plus 15 is what we shall add here to get, that's from I equals 1 to 3, to get FIDI, summation of all FIDI, and that will give us minus 30. Okay, so now when we do that, we are going to come over here to compute. So let's check again. So our di's were xi's minus a, just to confirm. 2 minus 5, the a gave us minus 3. 5 minus 5 gave us 0. 8 minus 5 gave us 3. So now FIDI's we had to compute, and that was 15 times minus 5 giving us minus 45. Okay, 10 times 0 giving us 0. 5 times 15, 5 times 3 giving us 15 rather. So now let's come over to II. What did we get for the assumed mean method? We obtained that it was summation from I equals 1 to n, in this case 3, FIDI all over summation FI from I equals 1 to 3, in this case, plus A. So this would imply that X bar will give us summation FIDI is minus 30 all over summation Fi, which is 30, okay, plus our A, and our A is 5, okay, our A is 5, so I'm going to put 5 over here, okay. So what that means is that X bar would now be 30 cancels 30 to give you minus 1, and minus 1 will add to 5 to give you 4. So using the assumed mean method, notice that we still obtained the same arithmetic mean. When we used the normal method, we got 4. When we used the assumed mean method, we got 4. Now let's come over to, I'm going to put it over here, that is III, obtaining the assumed mean, obtaining the arithmetic mean using the coded factor method. So let's come again to this table. We are going to develop, to start with, a colon for UI, and UI will be equal to DI all over C. Now, DI all over C means whatsoever we get as our DI, we will divide it by C. So what did we get as our DI here? It was minus 3, and our C is 3. So minus 3 divided by 3 will give us minus 1. What did we get as our DI over here? It was 0. 0 divided by 3 is 0. What did we get as our DI here? It was 3. 3 divided by 3 is 1. So we would now come over here to create a colon for FIUI. In this colon, we shall be multiplying each of our FIs with our UIs. So FIUI means 15 times 15 the frequency times our UI, which is minus 1, will give us minus 15. Then 10 times 0 will give us 0. That is our Fi times our UI. Then 5, our frequency, times 1 will give us 5. Okay, so here we can now compute from I equals 1 to 3. We can now compute our FI UIs, and that will give us that will give us minus 15 plus 5, that will give us minus 10, okay? Because minus 15 plus 0 is minus 15, minus 15 plus 5 is minus 10. So this adds up to give us this, okay? I hope you understand that. Now, the next thing to do is to come over here and write out the formula for the arithmetic mean in terms of the coded factor. So what we obtained was C U bar plus A. Remember, the U bar was summation FIUI from I equals 1 to 3, in this case, all over summation from I equals 1 to 3, I equals 1 to 3 of Fi, so plus A. Now, what is our C? Our C is 3. What is our summation FIUI? It is minus 10 all over. What is our Fi? Our Fi, if you remember, was obtained as 30. So if you put your 30 here, that gives you plus A. A is 5. So we would end up obtaining our x bar as 3 times minus 10 will give us minus 30 all over 30 plus 5. Now, minus 30 divided by 30 will give us minus 1. So we end up having minus 1 plus 5. And x bar will give us minus 1 plus 5 is 4. So we end up having the same arithmetic mean. So using the coded factor method, the assuming method, and the normal method all gave the same arithmetic mean. Okay? Now I'm going to tell you one thing before I end this video. Take note. This was the reason why we had exactly the same values was because we did not approximate. In the course of our computation, we did not approximate any value. If it so happens that approximations are involved in your computation of the assumed mean or the coded factor, of the arithmetic mean using the assuming method and the coded factor method, if it so happens that you make approximations, then it is very possible that your means will not converge to the same value exactly. That is not to say it is wrong. That is to tell you that because of the approximations, some values have been lost. So that will make your arithmetic mean method, the assuming method and the coded factor method produce values of the arithmetic mean that slightly diverge or deviate from the value produced by the normal method. Okay, so I'm going to stop here in this video, but like our video, share our video, and most importantly, keep subscribing to the channel because it makes the channel grow. And if the channel grows, it means we have the ability to produce more videos, more content for your consumption. Thank you very much, and God bless.